Okay, good. So this is, if you like, already complete formulation of Newton-Cartan geometry and gravity. But well, and it's fine, but it's maybe not fully satisfactory in the sense that, as I said, so part of the connection is indeterminate, but not all of it. So we would like to kind of pinpoint exactly what is the freedom in choosing this connection. Okay, so that's what we're going to do now. So okay, so let us pinpoint the freedom in the connection. Okay. Now here I will not do the derivation. Okay, I'll do the result. But even just to state the result, we will need some extra stuff. So to do this, we need to introduce the following objects. Another tau, but now we'll not index. Some other people call this V. And another symmetric two tensor. Okay, but now again with lower images. Okay. Okay. Now, so what are these things? Well, they should satisfy. So we're gonna demand that they satisfy this, if you like, completeness relation or orthogonality relation. Okay. Okay. New, and then one extra condition, which one also needs to impose to make sure that also this will very end guarantee that T mu H mu is 0. So they're also orthogonal in that sense. Okay. So you could take these equations as the definition of this object with the upper and lower images. Okay, so these are the defining equations, if you like, of these new objects. Now, there is a problem though, which is that these equations do not determine these objects uniquely. Okay, so this does not define mu and mu and H mu uniquely given. So the fundamental fields of tau mu and H mu. Okay, so if you give me tau lower H upper, then well, you can always find such tau upper H lower, but these equations don't determine them uniquely. We don't want to introduce even more arbitrariness, right? We're trying to actually. Okay, so we don't. This is already Newton-Cartan. Okay, we don't want to introduce extra degrees of freedom. You could, and then I think you end up with Aristotelian geometry or something like that. But so let's not do that here. Okay, so well, what are we going to do? Well, the point is that let us treat so to not introduce extra degrees of freedom. So again, this is different from the freedom in the connection, which is a physical degree of freedom, as I said, the Newtonian potential, for example, is part of it. Here, we don't want to introduce extra degrees of freedom. We treat the extra freedom as gauge. Okay, so I'm just going to introduce a gauge symmetry that's going to remove these extra degrees of freedom. Indeed, infinitesimally, d tau mu is equal to, so they will transform like this. So here I have chi, my gauge parameter, and I have this thing, okay, tau mu plus tau mu. Okay. Okay, so I introduce by hand this gauge symmetry, and I claim, and this is an exercise, that this removes exactly the freedom you have in solving these equations. Note, well, let me again, in view of time, maybe not write it out. You can actually find, so these are the infinitesimal transformations. It's not too hard to find the finite transformations, and there will be here an extra quadratic part in chi. Okay. Okay, so the linearized infinitesimal gauge transformations are these. Okay, so introduce them by hand. All right, good. But so now we have, so you can choose whatever tau upper and H lower you like. In the end, if our expressions are going to be gauge invariant, then it doesn't matter which one you choose. The physics will be independent of that choice. So that's great. Okay, good. So now again, statement without any derivation. There are some parts in literature where you can find the derivation. The compatible connection, so compatible torsionless connection has to be of the form as follows. So gamma mu rho equals, and there was already a question asking for this. So it's going to be tau rho d mu tau mu plus 1/2 h sigma d mu h sigma plus d mu h sigma minus d sigma h mu. And then, okay, so this would be completely fixed, but now an extra part minus h rho sigma k sigma mu mu, where, and this is the arbitrariness, k mu nu, which is an antisymmetric two-tensor, mu mu is arbitrary. Okay, so the arbitrariness finds itself, now we have found it, so not the full connection is undetermined, but, well, there is this part here, which is not fixed, it is two-fold, okay? Now, there is historically a long story about this, which I will just cut short in 1 second, okay? Okay, we will not take this fully as arbitrary. I'm going to assume this thing to be closed, and up to topological subtleties, really, I'm going to assume this thing to be exact. Okay. And again, if you come from the connection with GR, this will be automatic. If you want to kind of impose this in a covariant way, etc., there are things called Taylor's condition and whatnot, so I will not go there. But okay. So then, so now C mu is arbitrary. So actually, up to the, once I introduce this extra small assumption, then my arbitrariness in the connection has been brought back to a one form, which I call C. Many people call it M. I'm very sorry. Okay. Okay. Now there is still one more thing to be done, and then I can pause and make some comments. Is that a wait? So we said that, well, you know, there were these gauge transformations for tau and h. Okay, well, the connection should not depend on them, right? Because otherwise it would be, again, extra arbitrariness. So I should make the connection, okay, so delta chi gamma should be 0, and that fixes automatically for me the transformation of this gauge potential. So I get here that delta Cu has to be chi. Okay, so I have this extra gauge transformation that I also have on C to just to guarantee that the connection is invariant. Okay, so that I really didn't introduce any extra degrees of freedom. Okay. Right now, okay. So just I need to make a few comments here, of course. So the way I introduce it here is maybe not the most standard way. Okay, so I introduced this gauge freedom purely as a technical tool to let me invert the Newton-Cartan structure without introducing any extra degrees of freedom. Now, so this blue symmetry is sometimes called Milnor boosts. And also, actually, if you come from the gauging perspective, so you could also discuss this Newton-Cartan structure in the way Jan did, then actually they coincide with the Galilean boosts from gauging. Okay, so there are just two different roads to Rome, if you like. Okay. Right. Okay. Right. So I think it's now time to say. Okay. So let me summarize again Newton-Cartan geometry, and then in this second way. So Newton-Cartan gravity. Okay. Summary in the second formulation, which I will use in the rest of this lecture. Okay, so what do we have? We had R nu equals rho tau nu, and we have x double dot mu plus gamma mu rho sigma x dot rho x dot sigma equals 0. So these are the dynamic equations of Newton-Cartan and gravity, where these are equations for what? Well, the fundamental fields, if you like, in the second formulation are what? They are the one form tau mu, a special inverse metric h mu, and another one form c mu. Okay. So these are, if you like, the degrees of freedom of Newton-Cartan. Again, it's a bit tricky to really call them degrees of freedom because they still satisfy various constraints, but okay. Now, okay, so yeah, again, many of you are aware of this, but I just, for completeness, I have to point this out. Okay, so now we have this general fully geometric formulation. So let us go back to actual Newtonian gravity just for a second. Okay, so where is Newtonian gravity hiding? So in the special case, which actually up to gauge transformations you can basically always go to, okay, if you take these choices, okay, and then h ij equals delta ij, hij equals delta ij, ct equals phi, and all this other component 0. Okay, and again, I should probably put this in red. Okay, so actually, in the case where you make all of these things basically trivial or 0, and you just allow for the time-like component of the gauge field to be something non-trivial, phi, well, that is where the Newtonian potential sits. Okay, so the Newtonian potential sits there. Then, okay, so that gives you, so the Newton-Cartan equations become the actual, you know, Newton's equations, that the way we encounter them in the sample. Okay, so these two equations become just the Poisson equation and the Newton's second law for the gravitational force. Okay, good. Right. Now, okay, so we introduced a bunch of symmetries, so it's good to kind of list them. And again, they will come to play some role. First was that indeed now we have just a tensorial formulation, which, you know, by the standard rule of tensor calculus leads to a covariant or coordinate invariant formulation. So one, we now have a diffeomorphism invariant formulation. Okay, so all fields just transform like tensors. Okay, under this one, the connection transforms like a connection, but right. Okay, so these guys here, just by their standard index placements, they are tensors, and they transform the general coordinate transformations just as usual. So we have a general covariant formulation of Newtonian gravity. That's one of the main first features of Newton-Cartan gravity. Okay, two, well, we introduced the Milnor boosts. Okay, let's say delta chi. Let me not rewrite the transformations, they were here in blue. Yes, you can look at them once more. Okay, and then finally, there is one extra symmetry, which I didn't mention yet, is that, well, there is actually, I can make the following transformation. Delta C mu is just d mu lambda. So this is a U1, or should we rather say R? Okay, it doesn't matter. I think it's non-compact, but who cares? U1 gauge symmetry. Okay, where did it come from? Well, okay, so again, if you look at these equations, okay, really everything goes to the connection. Yes, the only way C enters in these equations is through the fact that it sits inside the connection. But if you go and look how it sits in the connection, it sits through its curvature K. Yes, and that's just a, you know, an abelian curvature. So indeed, if I shift C, I mean, again, so C is just the potential determining this field strength. So if I shift it with a closed form, nothing's going to happen. So there is this indeed this symmetry, since well, since C mu only appears to K, which is BC. Okay. So it's that, and it also means the physics is completely independent of this, and so there is really no physical meaning to this this gauge degree of freedom. So again, it's an extra gauge symmetry. Right now, again here I should make a comment that actually yesterday this has been encountered before. So if you would go take the approach as Jan did by obtaining Newton-Cartan geometry from gauging, then this coincides with the Bartman U1 via gauging. Okay, I have more to say about this, how this is related to Bartman U1, yes or no, etc. later, but at least in a simple setup without torsion, this is nothing but the Bartman U1. Okay, and then we're almost done, so we can move to GR and expansion. But just one final, well, two comments, just again to point out. So we have two equations here, right? Let's say A and B. So this is just a particle motion. It's kind of nice. There is a non-Lagrangian for this thing, which is has all the properties that you would like. It's coordinate invariant. It's parameterization invariant. H mu x dot mu over tau mu x dot mu plus c mu x dot mu. Okay, it's invariant under all these symmetries, under boosts, under U1, and under diffuse, and additionally it has representation invariance as well. So it's a very nice action. So if you vary this action, then indeed you end up with these equations of motion. Okay, so that's great. The particle equation has a Lagrangian formulation. Okay, that's not true for this other equations, and that's again different from GR, where actually the Einstein equation does come from an action. No Lagrangian formulation. Okay, right. At least not in the form that we have it here, and so I hope to come back to this later. That's why I mentioned it now. Okay, great. So that finishes basically my review of Newton-Cartan gravity. Okay, so this is Newtonian gravity in a current invariant formulation. And so our first goal will be, how can we get this out of GR? Well, if you like, as a non-relativistic limit, or more precisely, as the approach we'll take today, by doing a expansion powers of C of GR. Okay. Okay, so.
Dieter,
yes.
Can I ask a question?
Yes, sure, please.
So could you just explain some, is there any geometric meaning of this point particle? I mean, this fractional part, especially.
Well, I guess so. This is now a fine connection. So this is just, again, I would say geodesic, analytically speaking, auto-parallel equation for this particle.
So but so whether it's a proper length or not is not clear.
No, so that's the thing. So yes, so the thing it extremizes. Let's say this thing is more tricky, right? That does not necessarily have a geometric formulation. By the way, it's very easy that if you plug in this here, I mean, you really just get exactly the standard, action for a particle moving in a Newtonian potential that you know from everywhere. No, so yes, so again, it is. I mean, this still tells you that you move with parallel velocity all the time for this with respect to this affine connection. So that's what the equation means. But indeed, there's no longer a geodesic in the sense that it's a length minimizing, or I don't even know what's minimizing. So it's extremizing this thing. But indeed, I have no idea what this geometry is. But that's an interesting I agree. But,
I have another question. For the Einstein equation A.
Yes.
So left-hand side should satisfy Bianchi identity, I guess, as in any standard curvature.
Yes. So okay. So again, this curvature here will satisfy certain identities, Bianchi-like identities, and it's so again here. This is, by the way, again. So as I said, so I chose to choose, which is again here kind of the standard way it's written. So, but this is, let's say, the Ricci formulation of the Einstein equation. So you could go to some kind of Einstein version where you have some divergenceless object and things like that. I'm pretty sure. So yes, I mean, there is a whole story. So I will not talk much about the matter today. Actually, there is a very interesting story there. I mean, Jelle and Niels have some great papers about that. So there is indeed all kinds of conservation equations on the energy momentum tensor, also this expansion that, and they are all following automatically from Bianchi type identities on the curvatures, etc. Yes. So yes, there exist these analogs of Bianchi identities. That may not be my short answer, but I will not spell them out.
Okay, yeah. Thank you.
Sorry, Dieter. This condition on the two form K that it's closed or exact, whatever. Where does it come from?
Exactly, I impose it myself as so,
okay. So it's I suppose it's a condition on the curvature of this connection.
Sorry.
It must be a condition on the curvature.
Yes, exactly. So it's a rather complicated condition. So it's called, if I'm not, so there are two conditions. One is the Ehlers condition, the other one is the Trautmann condition. So there are mysterious conditions on the curvature. If you impose them, you can get rid of these extra things, and they basically imply this. Okay, but then again, you have to tell me why do you impose these conditions. So you could, but you can do it. But in a more modern perspective, I would say, there's no, it just imposes from the beginning. It just turns out that Newton-Cartan gravity just don't define it really with the most general compatible torsional connection. I mean, just define it to be the theory with this connection. Why? So there are two. Well, if you come from the gauging perspective, then again, this is automatic because you have this Barkman U1 that leads to this U1 gauge field. Or if you take the perspective as we do today, so as we'll see in the remainder of this lecture, if you come from GR, again, you'll end up not, you'll end up with this connection. You'll end up with C. Okay, so there is no room. So you could generalize, let's say, Newtonian gravity beyond with some cases which are not closed, but then you're just no longer doing really Newtonian gravity. You're doing some generalization of that, which is not something coming out of GR, for example. So there is not much motivation to do that. So that's why I will just ignore it and from the beginning.
Okay, but in principle, you could have Newton-Cartan structures which do not have K to close, right?
Yes, just like I could, you see, I mean, I could add to this now arbitrary torsion, and as a mathematician, nothing stops me from doing that.
Okay.
There is no good physical motivation. As we will see, there is one particular type of torsion, your intrinsic torsion, and the one we encountered that it's physically motivated to add it, so we will add it. But this is definitely not the most general torsion. Okay, so you could still say, okay, why don't you add the most general torsion? Well, I don't get it from GR unless there's a good physical motivation. Again, if you want to study, for example, couplings to condensed matter systems or things like that, then it might be of interest to actually generalize this and allow for more general torsion. But again, personally, I wouldn't call it Newton-Cartan gravity anymore. Then it's some generalized.
Oh, okay.
So I'll just take this as part of my definition of Newton-Cartan gravity.
Okay.
Okay. But yeah, that's something we can discuss.
Peter, may I also ask a quick question?
Sure.
Just because on the page you say mild boost is the boost of the gauging, but naively the mild boost I would count is 4 parameters, chi mu, and the boost is 3 parameters. So what is the?
Okay, very good. So there is actually this this extra condition which I didn't write. I'm very sorry. This gauge parameter is not free. It's
okay.
This extra condition.
Okay, that is.
Which I should have written. Thank you very much.
Okay.
That out. Yes. So it's only as actually 3 parameters. So that again, if you want to do it covariantly, you have to write like this, and then it satisfies this extra condition. Thank you. Yes, very good. Okay. Right. Good. So, all right. The 1/3 expansion of GR. So I don't think I will be able to finish this topic before the lunch break. So what let's see if we can do it. But so the plan is as follows. I will set it up quite generally. Then I will make this small assumption that will then bring us to Newtonian gravity. That will probably be after the break. And then once we've understood Newtonian gravity or Newton-Cartan gravity, we'll go back, relax this assumption, and then we'll end up with the PTSC story. And I hope to also say, well, at least the most important parts of that. Okay, good. So, well, as I already said all the way in the beginning, now we formally think of the metric as a function of a parameter C, which, if you're a mathematician, just take it dimensionless. just whenever you want to apply this to actual physical situation, you're going to identify this as the speed of light. And then for dimensional reasons, there will have to be some other velocity somewhere to again make these dimensions. Okay, so we're going to expand this thing, okay, in powers of c. So some notation here. Okay, so there's going to be some powers of c, and there's going to be negative powers of c. Okay, because c goes to infinity. Right, all powers can appear. I will call this the nth coefficient. So I'll denote this nth coefficient by putting a little n on top of it. Okay. And now, well, comes the point, and I will come back to this in a minute. Where does this expansion start? So you could naively say, well, we're going to do an expansion, you know, let's assume things be analytic, but no, you can allow poles. And so we're going to put here a -2. And I'll come back to this in a second why I do that. And then what I will do is I will do exactly the same for the inverse metric. So this is not what you're forced to do, but this is, let's say, what the history of the subject has taught us. Okay, this I guess was mainly Doku's idea. So then I'm also going to expand the inverse metric. Okay, in the same way, but again, note that we've already started putting some assumptions in here, which I'll point out now, is that, well, where do we assume this series to start? Okay, that it goes all the way to infinity, that's fine. But where does it start? Okay, so these are assumptions. Okay, and again, as I'll try to point out now, is that that's exactly, well, given by the intuition that this c should be the physical speed of light. So where is this based on? Well, take the simplest relativistic metric you will think of, which is just the Minkowski metric, right? Let's look at the Minkowski metric. And again, I'm going to use, and this is important, so my coordinates x mu are going to be t x I. Okay. So my first coordinate is going to be time, again, physically to the dimension of time, and I'm going to use the length for the spatial coordinates. So in these coordinates, the Minkowski metric takes the following form. Okay, there is a c squared here, and then there are just ones here. Okay. So we see here that, okay, if you just look at this absolute simplest metric, then indeed, well, you see that actually you have a power c squared here, so this thing actually diverges when c goes to infinity. Okay, and so it starts at, well, power c squared, which is n-2 here. Okay, so that's basically why we make this assumption. Okay, second, if we look at the inverse metric, it's of course absolutely trivial, but what you find is that then it looks different. Okay, and so you see that, well, now actually this is a negative power of c, so it's subleading. The leading order is actually here, which is the 0th order, and that's why we start the expansion of the inverse metric at order 0. Okay, right, and again, well, in some sense, so you could, again, this intuition stated differently, so you could define relativistic coordinates, let's say, where you would say, okay, ct xi, okay, and then of course, well, the whole point is that d2 x mu will come like c dt, okay, that's what x0, let's say, okay. I mean, the point is that if you want to work with an actual time, automatically dt will come with an actual c, and so that gives you the c squared here, okay, so the time direction will come with a c squared, and that explains why I make this assumption on my expansion. Okay? So here I'm now starting to put in some information that, you know, c is not just an arbitrary parameter, it really has the physical implementation of the speed of light. Okay, good. So, okay, right. Another assumption, okay, so we need to put in some extra stuff even further, is that, well, okay, we don't only assume the metric to start at order c squared, but actually if you look at this, it's only the time-like part that comes with order c squared. And again, here, you see, it's only going to be the dx to the 0 part that will go like c squared. All the rest will be subleading. So that means that actually the leading part of this thing is going to be one-dimensional. It's a rank 1 tensor, okay? Which means that we can assume that G minus 2, which is the leading part of the metric, is going to be, well, rank 1, and any rank 1 matrix we can write just as the tensor product of two, in this case, one forms or vectors, okay? So again, this we put in by hand, okay? This is just an assumption, a starting assumption, and again, well, you could take it as a mathematical action, or as a physicist, it is well, given by the intuition that I try to convey to you. Okay, right. Okay, is that fine? So this is the starting assumption of the non-C expansion. And we're going to make maybe later a few more assumptions, but all of those assumptions at some point we will relax. At no point will I ever relax these assumptions. Okay, so if you like, this is really the definition of what we will mean with the 1/C expansion of GR. Okay. And which makes it different from an expansion. I know you could do an expansion in terms of a cosmological constant or something, but then you would expect completely different behavior on how the metric depends on that ground. Okay, right. Now, okay, so well, expanding both the metric and the inverse metric is, of course, redundant, right? Because if you know the metric, you can just always find its inverse. And so these two series are just related, okay? They are in some sense the same series. So if you know one series, you could determine the other. However, and again, this goes back to Bokur. The point is that, well, sure, but instead of choosing just either one of these series, it turns out to be much nicer to choose a mixture, okay? So of degrees of freedom, some of them sitting in the inverse series and some of them sitting in the series of the metric. So that rather than pick one of the two series, okay, choose some fundamental, if you like, variables in each of those. Okay, so some of our degrees of freedom are going to sit in here, and some of them are going to sit in there, and some parts of this thing are going to be algebraically determined in terms of that. Okay, so it's going to be some mixed thing. This has historically been quite useful, in particular to make connection with Newton-Cartan geometry, but this is maybe not necessarily fundamental. Okay, so the choice of variables is something that I think even till today well, you should or you can think about. Okay, it's not clear if the best or the simplest variables have been chosen, but okay, I'll stick for the moment to just the variables that people have been, including myself, up to now. Right. Okay. So now what does it mean? So the point is that, well, okay, what connects the metric and the inverse metric is, of course, the fact that there is this inverse. Okay. So okay. So this you just plug in the two series. Okay, you'll find a sequence of equations. Okay, which is just that. You know, G n mu so let's say k, and then G n minus k mu rho equals 0 when n is not equal to 0, and then there is a special case that when G k mu G n minus k mu rho is equal to delta mu rho. Okay, so if you just plug in these two series without their coefficients, you see here there is also series, but it only has one coefficient, which is c to the power 0. So you equate the coefficients on both sides, and these are the equations that come out. And so now you have to solve this system of equations in terms of, well, your favorite variable. So you choose some degrees of freedom, and then other parts will be determined. Okay, so I will not do this in full generality. Indeed, I don't think you can do it in full generality. But so let's go step by step, and I'll show you how it goes in the first couple of orders. So, okay, let's start at leading order. Well, what is leading order? You know, this thing starts at order 0, this thing starts at order c squared, so the whole thing is going to start at order c squared. Okay, so then, well, there the equation is quite simple. It's just going to be what? Well, g0 mu nu, and then g minus 2 mu rho equals 0. Okay, but we already used, or that was our starting assumption, that this g nu rho was just tau mu. So this becomes equivalent to g0 mu nu tau mu equals 0. Okay, and indeed here we see immediately the Newton-Cartan structure appearing, because, well, so just rename, okay, g mu nu to be h mu nu. Okay, and now you see, so indeed it's a symmetric tensor, and, well, it has a no direction. Okay, so it has to be rank 3. It cannot be of lower rank, because otherwise the metric would not be invertible. So out comes a Newton-Cartan structure. Okay, so that's nice. And again, you see that to see the structure, you see that. So again, so let's point it out. So we have that. So it's important enough to kind of write it out like this. So leading order, we have the following. It's kind of here, but I guess I need to summarize this, because it's really the fundamentals of everything. Okay, we have identified our first set of degrees of freedom, if you like. So there is tau and there is h. They're completely free, because indeed it doesn't matter, well, apart from this condition. Okay, so they're an arbitrary Newton-Cartan structure. Yes. And so we see that indeed, but we see that to find them, some of the degrees of freedom, if you like, sit in the inverse metric, while some of them sit in the metric. Okay, so yes. Okay. Right now, okay. Okay, so now we want to move to next to leading order. All right. Okay. Okay. Leading order, next to leading order. Now, what is next to leading order? Well, it could be power C, actually. But things will get complicated, and so we're going to now make, again, yet another assumption. It's not fundamental, so let me not put it in red, but so. Okay. So we're going to assume that the metric is actually a function only of even powers of C. So of C. So this is purely a technical assumption. You don't have to do this, and indeed, maybe already at the end, I'll say a little bit about it. Okay, so you can relax this assumption to keep things simple, okay? Because if you don't make this assumption, well, things will become quite a bit more complicated. Okay, so to keep it simple. And it turns out that to get to Newtonian gravity, that's sufficient. Now, can you do that? Is this a consistent assumption? Yes, it is. And actually, well, I thought maybe to spend some time on explaining why it's consistent, but in view of time, let me not do that. You have to believe me, but there is this half hour, you know, before the next lecture starts or something. So if somebody does not believe me or would like to know more details, I can quickly sketch why you can always just consider only even powers. You cannot make an assumption that you're just going to consider only odd powers, right? That's not going to work. Only even powers you can do. Okay, so if you make this assumption, then the next to leading order will be order C to the power 0. Okay, otherwise it will be power C, and things would change. Okay, so let me maybe Yeah, we have 5 minutes, maybe a little bit more, so I can, I guess, finish this. Good, yeah, that's maybe a relatively nice point to finish. Okay, so if you go to next to leading order, so order C0, then you get the following equation: G mu nu minus 2, G2 mu rho plus, and now we also G mu 0, G0 mu rho equals, and again, remember the zeroth order was special because this delta comes at zeroth order. So now in this one case, we have here actually delta mu rho. Okay. So, right, now remember, this thing we know, it is minus tau mu, and also this thing we know is h mu rho. Okay, so what we don't know is this thing and this thing. And some of it will be free, okay, it's just, you can choose it freely, but some of it will be constrained by this equation. And we have to disentangle that to figure out what are the actual degrees of freedom. Now, okay. Okay, so to do that, it is useful, okay, to actually solve this equation explicitly. We're going to decompose G2 mu and G0 mu, which are the unknown components, into, well, spatial and temporal parts. But of course, well, so again, if you go back to Dokur, that's what we would do, but we would make a choice of coordinates. But so we're going to improve a little bit on Dokur here, and so we're going to do this without making a choice of coordinates. Okay, so we're going to do this in a covariant way, but that's good because at this level we already have tau, which gives us, by the way, I think I forgot to mention this, but assume you already know, but tau gives us a sense of direction of time, while h essentially provides a spatial metric. So again, this was mentioned by Jan yesterday, so at least those that yesterday are aware of this. Okay, so how does that work? Well, basically, we can write G mu nu, for example, as follows, and this is completely general. Well, I can have a part which has a leg along tau, okay, and then I will introduce another part. Let me call it Q mu nu, where I'm going to assume that Q mu nu is purely spatial, meaning that if I contract it with tau, it's 0. So again, I don't show it, but it's not hard to convince yourself. So again, using all the way back, I mean, this relation here, you can think of as two projectors, a time-like projector and a space-like projector. And using this projector, you can decompose any tensor in this way. And what we end up with is the decomposition of this form. Okay, so I skip some details here, but it should not be too hard to convince yourself that you can always uniquely decompose something like that. And again, we do the same thing for this guy. Okay, but now with upper indices. Oops. Here. 2 tau mu, and then we call this thing mu plus mu, where again we make the assumption that mu is spatial. Okay, right. So you can decompose any tensor like that. So this is no assumption or nothing. It's just a way of writing things. And now what you do is now you plug this in. You use the properties of the taus and h's, okay, lower, upper indices, whatnot. And then what you find is that you can uniquely solve this as follows. So then, okay, so you plug in. Okay. If you plug that in there, then what you find is that, well, actually, well, indeed, nothing happens to this temporal part. This C is completely free, it's not constrained. But the Q part here is actually completely constrained. It has to be H mu nu, something which we already know. Okay, it is defined through this invertibility relation with respect to the H with upper. And then also we find that if you do this, then you get here actually tau here. So P here has to be tau upper. Okay, so what you find, well, or at least its tau component has to be that, and then its spatial part. So this is mu, and then mu. Actually, you see. So the point is that you see this thing here is free, but then through this relation, it determines this part of the inverse matrix. So C again appears here. Okay. So now that the temporal part of this thing here is fully fixed. So the spatial part of this thing is fully fixed. Here the temporal part is fully fixed, and indeed I don't know why I call it P, but okay. So just call this from the beginning beta. I'm going to call it beta. So that I stick to my own notation, which is maybe a bit outdated. Other people call it phi or whatnot. So, all right. So the point is that this here is left free by this equation. It doesn't. This can be arbitrary, and also the C here can be arbitrary. Okay, but other parts of this metric components are completely fixed in terms of this. Okay, so we see that at this order. Oh well, okay, so let me maybe just summarize. Okay, and then again, might be to stop like this. So summary. Okay. So so if you go to leading order and next to leading order in the even power expansion. Okay, so we have G minus 2 mu nu, we have G0 mu nu, we have G 0 mu nu, and we also have G2 mu nu, okay? But they're not independent, okay? They are distinct to distinct. So actually see that really what they are determined are is in terms of what? Well, we have tau mu, H mu nu, an extra field C mu, and an extra field delta mu. With the condition that, again here, maybe let me fix that consistent, with beta satisfying this algebraic condition. Okay, so this is basically the first important upshot. Now, okay. Now you can go on, move to next leading order, etc. You can keep on for infinity. So this is a procedure that you can always run, and you will always find at each level this new field, but well, it becomes a bit tricky after a couple of orders, of course. So for today, it will be enough to stick at this order. Okay. So now the plan is basically just plug this thing into the Einstein equation and see what we get. But again, I think in view of time, it's probably better to do that after the lunch break. Now, again, let me already, well, it's kind of obvious from my notation. So it will be no surprise, but well, we see here appearing exactly the Newton-Cartan fields. Okay. Good. So we see them coming out of these metric components. Still, there is no dynamics, of course, but that we'll get from expanding the Einstein equations. Okay. And then it's interesting. So already here, there is something extra. And what the meaning of that thing is, well, we'll also discuss. Okay, but all of that is for after the break. Yes. So yeah, I think this is a good place to stop. Are there any comments, questions?
How is it that you see that this C is the same one that you introduced before? You just plug it into the connection and compare? Or?
Oh, no, well, for the moment, we don't see anything.
Yeah, but I mean, you could imagine, I mean, you have a metric, right? So you have a Relativity connection, you can just then compare, I suppose, the...
Well, yes and no. So yeah, we'll get there. So indeed, so as we will see, so how can I identify this C as the C of Newton-Cartan? At the moment, I cannot, but there are two ways to do it, and rather equivalent. One, it will have exactly the same symmetry transformations as the one of Newton-Cartan. So we will have, the blues, the diffeomorphisms, and the U1, as we will see. Second, indeed, as you say, it appears exactly once in the equation of motion as the C of Newton-Cartan will appear, namely through the connection with this curvature.
Okay, but at this rate, at this moment, C is something you introduced.
Yes.
Okay, all right, thanks.
Right.
Any other question?
again, I mean, so just okay, it's a small point, but so I didn't introduce C in sense, right? It comes out of the relativistic method. I mean, I don't have a choice. I have to include it. Yes.
No, I meant the fact that you chose to call it C.
Yes, very good. So the fact that I call this out C is, of course, yes, mysterious foresight.
If there is no more further question, why not thank Dieter, and we have a lunch break. Thank you, Dieter.
Thank you. I should stop recording.